Welcome to The Explainer. Today we're diving into a literal mindbender. We're going to trace the historical evolution of quantum physics. And honestly, this isn't just about complex math or dry historical dates. It's about a fundamental, ground-up shift in how human beings understand the universe.
To really get into the weeds, we're grounding our explainer in an incredible piece of source material, the Arabic translation of Werner Heisenberg's Physics and Philosophy. Heisenberg wasn't just sitting on the sidelines observing the quantum revolution. He was literally one of its chief architects. Through his writings, we're getting a direct, front-row seat to the intellectual earthquakes that completely rocked the scientific world in the 1920s and 30s.
So before we get into the history, I want to ask you something. What if the world you see isn't actually there until you look at it? Just sit with that for a second. In classical physics, a billiard ball rolling across the table has a definite position and speed, whether you're watching it or not, right? But as we're going to see, the pioneers of quantum theory discovered that at the atomic level, objective reality as we know it completely dissolves.
Okay, let's dive into this. Here's our roadmap. We're going to start with the birth of quanta, then cover the atomic revolution, wave-particle duality, the new quantum mechanics, the uncertainty principle, and finally, wrap it all up with the Copenhagen interpretation.
Section 1. The birth of quanta. Breaking classical physics. Picture it. It's the late 19th century. Physicists are feeling pretty confident. They felt they had a rock-solid grip on the universe, using Newton's mechanics and Maxwell's theories of electromagnetism. But there was a glaring issue. Classical physics completely and utterly failed to explain thermal radiation, basically how heated objects emit light. And because of this one crack, the entire classical foundation crumbled incredibly fast. In just 24 years, a rapid-fire succession of discoveries turned science completely upside down. It kicked off in 1900 with Max Planck, accelerated with Albert Einstein in 1905, was applied to atoms by Niels Bohr in 1913, and culminated in a massive paradox thanks to Louis de Broglie in 1924.
To really grasp this timeline, we've got to define the concept that started the whole avalanche: quanta. Basically, these are distinct, indivisible packets or bursts of energy. Back in the summer of 1900, Max Planck realized the only way to mathematically solve the thermal radiation problem was to assume energy doesn't flow in a continuous, smooth wave like water, but rather in distinct, choppy bursts. Heisenberg actually recounts this famous anecdote where Planck was taking a walk in the Grunewald forest with his son, and he confided that he felt he had just made a discovery of the first order, maybe the biggest thing since Newton. And he was right. By 1905, Einstein took this a step further, proving that light itself actually travels in these discrete packets. That completely changed the rules of the game.
Moving to Section 2, Revolutionizing the Atom, Rutherford and Bohr.
And this brilliantly illustrates how the scientific community pivoted. Once they proved light behaves in these strange quantum packets, physicists shifted their focus to the very structure of matter itself. In 1911, Ernest Rutherford figured out that atoms have a dense, central nucleus with electrons orbiting it, kind of like a tiny solar system. But there was a catch. Classically, this model made zero sense. According to the old rules, orbiting electrons should lose energy and just crash straight into the nucleus. So, in 1913, Niels Bohr swoops in and rescues Rutherford's model. He proposed that electrons are forced to obey quantum rules. They exist only in distinct, fixed, stationary states. They don't crash, they just instantly jump from one fixed orbit to another. This is huge because it finally explained the incredible chemical stability of elements. A carbon atom stays a carbon atom purely because of these rigid quantum rules.
Section 3. Wave-particle duality, the great paradox.
Now, what's really interesting about this slide is the sheer cognitive dissonance it represents. By the 1920s, the physics community was tearing its hair out. The experimental results were pointing to a total, unexplainable contradiction. On one side, you have particles. They're point-like, they have a definite position and momentum, and they act like tiny billiard balls. But on the other side, you have waves. They're spread out over a large space, characterized by frequency, and they interfere with one another. Then, in 1924, Louis de Broglie drops a bomb. He proposed that not only does light act like both, but matter itself, stuff like electrons, also exhibits this dual behavior. I mean, think about that paradox. How on earth could an electron be a concentrated point of matter and a spread-out wave at the exact same time?
Which brings us to Section 4, the new quantum mechanics, a mathematical resolution. The physicists desperately needed a way out of this paradox. They realized it was time to stop relying on pictures in their heads and just trust the math.
And the breakthrough came in a rapid 1-2 punch. In 1925, Heisenberg invented matrix mechanics, which was a purely mathematical system that threw the whole idea of physical electron orbits right out the window. Just a year later, Erwin Schrödinger developed wave mechanics, and shortly after that, Max Born introduced the crazy idea that these weren't physical waves of matter we were dealing with, but probability waves. The kicker? Schrödinger's and Heisenberg's models were proven to be mathematically equivalent. They were literally two different languages describing the exact same truth. But don't miss the massive philosophical shift here. The math was no longer describing definitive paths. It now relied purely on statistical probabilities.
Section 5. The uncertainty principle. The limits of knowledge.
So, the crucial point is how this reliance on probability leads us directly to the most famous limitation in all of physics, the uncertainty principle. Formulated by Heisenberg, it dictates the fundamental inability to simultaneously know both the exact position and the exact momentum of a quantum particle. Basically, if you measure the position of an electron with extreme precision, you completely lose all knowledge of its momentum, and vice versa. And it is absolutely crucial to understand this next part. This is not a flaw in our measuring tools. It's not human error. It is an inherent blurriness built into nature itself. The particle simply does not possess a definite position and momentum at the same time.
Let's walk through Heisenberg's famous thought experiment step by step to prove why this happens. Step 1. Imagine trying to observe a single electron using a super high-resolution gamma-ray microscope. To see the exact position of the electron, you need to hit it with a very short wavelength of light, like a gamma ray. Step 2. That high-energy gamma-ray photon physically strikes the electron, so it can bounce back into your microscope lens. Step 3. That very impact violently alters the electron's momentum in a completely unpredictable way. So by the time you've measured it, it's already gone. The very act of measuring the position permanently destroys our knowledge of its momentum.
Now, as you might guess, this statistical, unpredictable reality deeply troubled a lot of scientists. Albert Einstein famously declared, "God does not play dice." Einstein heavily favored a deterministic world. He strongly believed there just had to be deeper, hidden variables we simply couldn't see yet, and he fiercely rejected the idea of inherent randomness. Heisenberg, on the other hand, argued that this unpredictability was a fundamental, unavoidable trait of the universe. It was an intense, profound clash between classical certainty and quantum probability.
And that leads to Section 6, the Copenhagen Interpretation, Philosophy of the Quantum.
Let's move to the Copenhagen interpretation and see how this builds into the ultimate philosophical conclusion. Working together in Copenhagen, Niels Bohr and Werner Heisenberg synthesized all this math into a cohesive philosophy. The cornerstone of their interpretation is complementarity. Bohr argued that wave and particle behaviors are mutually exclusive, but they are equally necessary to understand the whole picture. You can't see both at once. Crucially, it is the observer's choice of experiment that decides which face the quantum system reveals. Set up a wave experiment, it acts like a wave. Set up a particle experiment, it acts like a particle. The language of classical physics completely fails us here. The system genuinely does not have an objective reality independent of our measurement.
Which brings us right back to our opening thought. If the act of observation, the physical interaction with a measuring device, essentially forces reality to snap into a definitive state at the quantum level, what does that mean for the universe when no one is looking? Einstein's writings show us that science doesn't just quietly discover nature, it actively interacts with it. We're not just spectators, we are active actors in the great drama of existence. I hope this explainer has left you as completely fascinated by the history of the quantum world as I am. There is just so much more to learn. Thanks for joining me today, and keep questioning the reality around you.